Hello, my name is Nolan Kelly. I'm going to be presenting with Jennifer Escobar, Jackie Zhu, Pei Chen, and Yunting Zhu. We are all master's students at UC San Diego, and we're going to be discussing wastewater treatment and optimizing the best time for adoption of wastewater treatment. First, my colleague Jennifer is going to discuss the issue that we researched.
So cities typically use either decentralized septic systems or centralized wastewater treatment systems to take care of their waste. Now, decentralized septic systems are typically hooked up to individual households or buildings and only manages the waste for that individual household. This is typically associated in rural areas that have smaller populations and less dense populations. On the other hand, we have wastewater treatment facilities which link every individual household in a given city to a central wastewater treatment facility that collects the waste from these houses and oftentimes treats this waste in order to be repurposed for different uses. Now, wastewater treatment facilities are typically associated with bigger cities that have much more dense populations. Now, our central question today is, when would be the optimal time for cities to transition from these decentralized septic systems to wastewater treatment facilities? Now, wastewater treatment facilities are costly in their creation, and it's costly to hook up every individual household to one treatment facility. Therefore, it is a large burden on cities, especially cities that are smaller and that have less of a budget. Therefore, we want to look at what would be the best time for especially those cities to take on this expenditure.
Next, I'm going to pass it over to Yunting Zhu to discuss our methodologies.
Yes, I will introduce the methodology of our research. Next slide, please. Here is our overall model. The model is essentially has two parts, including actual data for small cities in Oregon state and the critical parameters of the model so that we can get the optimal timing for the wastewater treatment plant construction. Next slide, please. The parameters are coming from articles and public databases. Here we want to thank the League of Oregon Cities for providing us most of the actual data for small cities. Then some of our variables are regression determined, like city budget, collection system, and housing density. The main model we referred to is from Campa. The research is for Italy, specifically for the island of Sicily, where has the same climate as Oregon. In our model, we referred to the machinery cost and architecture cost from this paper, which is our main parameters. The paper has 9 different types of machinery cost models, so we consulted professionals to simplify it into 5 cost models. Another main model we utilized is from the city of Raleigh, North Carolina, for the collection system, specifically for the pipe cost, which is the actual bill charged by a construction company. Next slide, please. Here are our estimations for housing density, cost, city budget and pipe costs. We used the population as our independent variable to do the simple linear regression. We also had a log and a squared transformation to get better estimations. All R squared for the regressions are fairly good. Then we used the parameters from outside models we used to predict machine and architecture costs. Finally, we need to minimize the overall expenditure or cost on wastewater treatment plant construction with respect to the city budget to get the optimal timing for the cities.
So I'm going to hand things over to Jackie Zhu, who's going to discuss some of our quantitative outcomes.
we broke the total cost down and we found that the collection system cost dominates. It takes about 96% of the total cost. And it is because it's very expensive to bury pumps. Next, please. And for the construction cost of wastewater treatment plants, it only takes 5% of the total cost, and the architecture cost is the primary driver. It's because as the population grows, we need more basins and more collection ponds for holding the wastewater. Next, please. In estimating the optimal timing, the blue line is the total cost and the orange line is the estimated city budget. In the very beginning point, the cost is 50 times to the city budget, but starting from 3,000, the ratio becomes asymptotic, and in 10,000, we can find that the cost and city budget are very close to each other.
So now me and my colleague Pepe are going to discuss some of the conclusions. So as Jackie mentioned, you can see that cost to budget ratio following an asymptotic decline, and it bottoms out at about 0.4 because of some fixed costs we have involved in the model. That asymptotic decline really represents a reduction in borrowing costs because it is sort of the cost of investment in the total project that needs to be financed through bank loans or through issuing of bonds. And so essentially, if you were to invest in a wastewater collection and treatment system before about a population of 3,000, you would be essentially spending a lot of money on interest on your loans or bonds. Now, if you wait too long, conversely, right, if you wait too long to invest in this type of system, you might not receive the type of economic development that you're looking to receive as a city. So while there's not really a hard upper cap on the range of population where it's optimal to invest, there certainly is a hard lower cap at about 3,000, because if you get any lower than that, really the system in relation to the overall city's ability to afford a system like this really becomes too expensive. So now I'm going to pass things over to Pepe, and Pepe is going to discuss some of the limitations of our model.
Okay, so we have three limitations on our model. The first one is for simplicity. That means that our model only considers initial construction, and it means that we did not put expansion or growth into our model. The second one is heterogeneity of city. It demonstrates that different cities have different factors, such as industry. Different industry use water differently, and also weather is another factor, and population growth model is another consideration too. The third limitation is environmental damage quantification. To be a if we did not put the externality into our model, let's imagine if we're in Los Angeles, then there's a great population, and if everyone is using septic system, there will be a great amount of sewage and other pollutions. Yet, we didn't put these externality on environment into our models. So we think that for further research, these three factors could be put into consideration. Thank you.
Yeah, thank you so much for taking the time to visit our poster and listen to our discussion, and we hope you enjoy AiChe.